So we've mastered the skill of writing equations for what happens when substances dissolve in water. Now for the more exciting part, we're going to combine those solutions and have them react with each other. Now there are many chemical reactions in the world, and we will not be able to master all of them. In years you wouldn't be able to do that. But there are a few reaction types that are so reliable that we will be able to master them. So we're going to start with predicting the products of precipitation reactions. And if you haven't already watched the video from YouTube of somebody mixing silver nitrate solution with sodium chloride, stop, go back, and watch the picture of them mixing things in the test tubes. What you'll see in that video is that a solid forms where there was no solid before. That's a precipitate. That reaction was a precipitation reaction. What we're going to do is learn to write the chemical equation for what happens to produce that precipitate. And the key to doing this, I think the key to writing a lot of different chemical reactions, is to try to visualize what's really happening in the flask. I think it can be so dazzling for these symbols to dance on the page. We have to tie them into a physical representation. So what I'm going to do is actually draw little flasks or little beakers or little test tubes as they had in that video. Maybe I'll have mine in beakers. Let's translate what the equation says about the reactants and show what's really in the flask, what's really in the beaker. So what I see there is silver nitrate. I see a metal and a non-metal. I see an ionic compound. It's soluble, it's dissolved in water, so I know that what's really swimming in the solution are silver ions and nitrate ions. The other thing we have before the reaction is a solution of sodium chloride. Again, metal and non-metal, ionic, so I've got sodium ions and chloride ions. Now what we're going to do is mix them together in another beaker or in a test tube. And in the split second before those substances have a chance to react, I'll just have that mixture, silver and nitrate and sodium and chloride, swimming around. So that's my picture of the left-hand side of the reaction equation. That's what's swimming in the flask. All right, now the reaction is going to happen, and what you observed in the test tube is that a solid formed in the flask. And if we wait long enough, it'll settle out to a lump in the bottom. We want to know what that solid is so we can write the products in our reaction. Well, let's see what the possibilities are. In an ionic compound, a positive ion is always present with a negative ion. So looking at this before here, all the positives and negatives together, I could have silver with nitrate, or silver with chloride, or sodium with nitrate, or sodium with chloride as my products. But wait a minute, we can rule two of those out right away. I know silver nitrate isn't the precipitate. From the very beginning, I had a homogeneous solution of silver nitrate. Silver nitrate dissolves in water. Similarly, sodium chloride can't be the product. So my potential products are silver chloride and sodium nitrate. This is an example of what I call an exchange reaction. But it goes by other names as well. You'll even see that on the video that you watched before this. They're also called double displacements or double replacements. Because what we can see is that the ions exchange, or they swap partners. The positive of one goes with the negative of the other. The positive of one goes with the negative of the other. Almost done here though. I don't know which of those two potential products, silver chloride or sodium nitrate, is the solid. And what I'm going to need to solve this is a table that will be provided to you anytime you need it. This is a table of solubility rules. And as I say, we don't memorize here. I will provide you this table anytime you need it. Your job is to learn how to use it. What we're looking for is to decide whether silver chloride or sodium nitrate form the precipitate, whether they come out of the solution as a solid, whether they are insoluble in water. So I'm going to look for any one of those 4 ions in the central column. And what I can see here is that sodium ions fall under the category of soluble ionic compounds. So that's not the solid. That's going to stay aqueous in solution. What else do I see? Chlorides are solid, but note that there's an exception column. Compounds with silver plus and chloride together, those are an exception to the soluble ionic compounds. That means silver chloride is insoluble. It's a solid and it precipitates. So now I can go back and finish my equation. Silver chloride is solid. It's the precipitate. And the sodium nitrate is aqueous. That's all there is to it, my friends. While I'm here, though, let me show you a few different styles of writing equations. There are 3 different styles, and the one that we wrote already was called a molecular equation. I'm copying here exactly the same equation we worked out on the other slide. I wish it wasn't called a molecular equation because there are no molecules in this whole thing. What they mean when they say molecular equation is that you don't see any charges. Although there are ions present, they're disguised when I pair the positive and negative ions together in the formula. Now, there's another style of equation called the complete ionic equation. Sometimes it's called the total ionic equation. And what I like about that kind of equation, it's a more realistic representation of what's really swimming around in the beaker. We're going to show here exactly what we showed in the pictures of the beakers. So when I said I had a beaker full of silver nitrate aqueous, because it was ionic, what we really had was silver ions and nitrate ions. So now I'm going to translate what it means when I say sodium chloride aqueous. A soluble ionic compound gives me ions in solution. Continuing my translation, on the product side, I have silver chloride. It's ionic, but wait, it's a solid. It's not swimming free in the solution. It didn't dissolve. It's sitting as a lump in the bottom of the beaker. You leave that stuck together because it's a solid. And finally, sodium nitrate aqueous, ionic compound dissolved in water, aqueous. That gives me the ions in solution. So that's the complete ionic equation. That shows all the ions as they actually are in the beaker. The next equation is called the net ionic equation. And I think you know what net means. If you get a paycheck, you know the difference between your gross pay and your net pay. The net is what's left over when we get rid of everything that doesn't matter. The fancy name for what doesn't matter here is spectator ions. You'll see in the complete ionic equations that some ions are exactly the same on the reactant side and the product side. I've got nitrate on the reactants and the product side. I've got sodium ions exactly the same on the reactants and the product side. Those are called the spectator ions because they just stand around and watch. The complete ionic equation I write by leaving out the spectator ions. that silver ions plus chloride aqueous gives me AgCl solid. I like the net ionic equation. It points out the fact that the sodium and the nitrate obviously aren't doing anything. The molecular equation makes it look like you make sodium nitrate, but you don't. They are just spectators. Let me go back to the picture of my beaker. Let me see. Let me label in the bottom. Now, we said silver chloride was the solid, so that's what's there. But that had nothing to do with the sodium ions and the nitrate ions. Those were the spectator ions. The molecular ion makes it look like you made sodium nitrate. Yeah, sodium nitrate aqueous is sodium ions and nitrate ions swimming around. That's exactly true. But it's not so much that we made it, it was just there all along. So back to my slide of all three styles of the equation. Which equation is the right one? They all are. Now for you starting out, I want to make sure that you will know be able to write all kinds. So I may ask you questions where I specify which kind of equation I write. If I don't specify what equation I want you to write, you have your choice. And again, different ones have different uses in different contexts. I like the net ionic equation. It really cuts the clutter out. The molecular equation, though, is helpful to show me which bottles to pull off the shelf. Which solution is the source of my silver plus ion? The silver nitrate solution is. And the complete ionic equation has virtue as well. It's the most realistic picture of what's happening in there. So I hope we'll get used to going back and forth between the different styles and using the one that works best in the context that we have. So there's my first example of writing equations for a precipitation reaction. Before I practice with some more, I want you to stop here and watch the next video that shows something happening in the test tube.